First of all, to be honest, personally, I'm very happy of this lecture. Beside everything, beside the GI or our student chapter, personally, I'm very happy to have you today.
Thank you.
Let me start to welcome everyone. Thanks for being with us today for this very valuable lecture by Professor Kyle Rollins. This lecture is a part of the Cross USA lecture tour for 2024. The lecture is about identification and treatment of the collapsible soil and will be delivered by the distinguished Professor Kyle Rollins. Professor Rollins got his CS degree from Brigham Young University and his PhD from University of California at Berkeley. After working as a geotechnical consultant, he joined the civil engineering faculty of BYU in 1987, following his father, who was previously a geotechnical professor. He has supervised more than 130 graduates and published over 190 papers. I guess this number has increased nowadays. By the way, Professor Kyle Papers was one of my main references during my PhD. He was working in the drilling shaft, and his papers really was beneficial for me. His research involved liquefaction assessment of gravel, lateral resistance of piles and pile group, passive resistance of bridge abutment, lightweight cellular concrete of retaining structure, and various soil improvement techniques. His studies typically included full-scale testing to determine ground truth behavior with an apparent love for the high-energy environment. Professor Rollins studies dynamic compaction for treatment of collapsible soil, which is the main interest of our today lecture. Professor Rollins was the chair of the Geotechnical Technical Committee on Soil Improvement, and ASCE has recognized his work with Hoover Research Award, Wellington Prize, and the Wallace Howard Baker Award in 2009. He was a cross-Canada geotechnical lecturer for the Canadian Geotechnical Society, and more recently, he received the Outer Governing Medal for Science and Technology and Osterberg Innovation Award from the Deep Foundation Institute. For sure, very wealthy biography. And to be honest, as I mentioned, I was one of your students remotely through your papers. It's a great pleasure and honor to have you today, Professor Kyle. I will not take too much time. I will leave the floor for you to start this valuable lecture. Thank you.
Thank you for the kind introduction. That's very nice. It's a pleasure for me to be with you today. Let me see if we can get this all working here. You see that okay?
Yes, we can see the screen now.
Okay, wonderful. This is a photograph of my university, Brigham Young University. We're located right up against this mountain range that was formed by earthquake faulting. So earthquakes are a big issue for us. We have a student body of about 30,000 students, and we're a private university. So this makes us about the largest one of the largest private universities in the United States. We're located in the state of Utah. That's highlighted there. I'm sure you've seen California before. We're just a couple states in. Utah was the site of the 2002 Winter Olympics, and we've been selected for the Winter Olympics in, I think it's 2032 or so. So we're having a good time here. There's California. Utah is home to 5 national parks. A lot of people come from around the world to see these spectacular geological formations like Delicate Arch here, which is about 80 meters tall. And you can walk right up to it and stand underneath it. It's very beautiful. We hope sometime you might be able to visit us. We'd love to host you.
Thank you so much.
BYU is 12,400 kilometers from Riyadh. So it might seem like we're far, far apart, distant from each other. But if you have the right perspective, you'll see that BYU and Riyadh are very closely located to one another. And the way the world is shrinking every day, the opportunities to work remotely with each other via the internet makes the world a whole lot smaller and makes us all neighbors.
Yes.
Today I'm going to tell you something of what we've learned about collapsible soil identification and mitigation. This is a process that's gone on for a while. We're still learning, of course, like you. The definition is collapsible soils are soils which are relatively strong and stiff in their dry natural state, but they can lose strength and settle dramatically when they become wet. So what's the reason they have this dry strength? There's a couple mechanisms that could account for this. One is negative capillary pressure. If you look at soil grains situated like this, as the soil tends to dry out, the water retreats to these interstitial connections, and the water pressure becomes negative. And as the water pressure becomes negative, if we look at the Moore-Coulomb strength theory, it says that the effective stress will go up, which will lead to an increase in shear strength. Now, if the soil becomes wet, that water pressure increases and the shear strength decreases, allowing the soil structure to become weaker and to settle. Another mechanism is cementing agents like calcium carbonate, for example. They might form at these joints and strengthen the structure. So these cements will increase the cohesion, and that increases the shear strength of the soil particles. Now, if again the soil becomes wet, the cement can degrade and the shear strength can decrease so that it could settle or lose strength. So there's a lot of damage that results from collapsible soils. This is a photograph of interstate highway in Montana, and you can see all the bumps and troughs as someone's trying to drive a car along here. It's more like a roller coaster than a highway. Now, our maintenance people do their very best to keep this level with time. They fill in the areas that are low. And when they went to repair this highway, they found out that there were sections with 43 centimeters of asphalt pavement in the effort to keep it level. So this required a very high annual maintenance cost. And you can see if you're driving along this very fast, your car might lose contact with the roadway. Now, we're not alone here. I found this morning a photograph from Saudi Arabia where it looks like you're having similar problems. And the reason these are irregular is because the soil might get wet in one zone and not get wet in another location. And as a result, you see these bumps and troughs. This can also cause damage to houses as water runs off and is ponding in a corner underneath the foundations. That can cause it to settle and cause cracking in the structure. This photo on the right side is more serious. This is a crack that goes through an earth dam. It was designed, the dam, of course, is designed to prevent stormwater runoff. And when the collapsible soil became wet, there was a big crack between the soil that was collapsible and the soil that wasn't, right through the dam. So this can cause some real significant concerns. There are different types of collapsible soil that people talk about. One is loess. People pronounce this in different ways, but that's how I learned it. There's also alluvial fan deposits and loosely placed fills that we don't compact enough. So in the United States, we have large areas of loess soils along the Mississippi River and Missouri River, and in states like Washington and Idaho here. But there's a lot more of these collapsible alluvial soils. These blue dots show locations where alluvial fans have had collapse take place, and primarily in the Western United States. I looked on some papers here and found that there are certainly collapsible soils in Saudi Arabia. I'm sure you're more aware of that than me, with all these blue triangles. And I got this from a paper by Defala and Al-Mabashi. Here's some photographs of the vertical slopes that often develop in loessl soils. The cementing often takes place on root holes and vertical planes. So the soil wants to stand vertically. And you can see these in China, Washington, and Mississippi. These stiff, dry soils, cemented to a certain degree, will stand nearly vertical. And you can see here the drainage has been put in place to get the water out of this slope so that it doesn't settle if it were to become wet. Here's the geological setting of collapsible alluvial soils. These were primarily alluvial fans at the base of mountains. It may also be the slope wash that's labeled Z there, it's in the blue, running off of the mountains, or infill fans. And these can coalesce together. So in this S zone here, it can cover a large area. Now they're often developed by mud flow, and I took this photograph after a wildfire that removed some of the vegetation upstream. And in the spring, when there was a large storm, the silt and sand were washed down into the valley here. Now, this is a little schematic I put together that shows the flow coming off of a mountain front. And that soil can come off in a very fluid state, very loose. And then over time, it dries out before the next period of deposition. So the next event, it may be 10 years later, who knows? That soil now is very dry and stiff. And even though this additional weight is being placed on it from mud flow, the soil underneath that doesn't really settle very much. It's in a stiff, dry condition. And then that new layer dries out as well. And this process can repeat itself so that you can build up thick layers of collapsible soil that really haven't had a chance to consolidate in their wet, saturated state. Okay. So you'll often see that they have a very porous structure. This is pretty obvious, some of these holes, but many times they're just small diameter holes that were formed as the air bubbles get out of the soil structure during deposition. But not only is it porous macroscopically from the naked eye, but it's also porous from microscopically, and these are some electron micrographs that I took with my students. And you can see that those open holes where the structure is just being held together by some clay particles. And looking a little closer at it, you can see these open void spaces with some clay particles at the joints holding the thing together. So how could we identify these? Well, we already know that where they might be located in loessl soils or alluvial fans. But there are other factors. We can look at some geomorphic factors that our geological friends have helped us identify. We may have some clue based on the soil type. We can get some idea about based on the soil density and the moisture. They're usually low unit weight and low moisture content that are collapsible. We can also take samples and test them in the laboratory to see how much they're going to strain under load. And if that's difficult, we can use in situ collapse tests. So I'll briefly review this, and I'll spend more of the time talking about how to solve the problem. So some of the geomorphic factors that increase collapse are that it's more likely to be collapsible if the drainage basin area is less than about 75 square kilometers. Statistically, these are primarily from studies in the Western United States. It's likely more collapsible if there's mudstone or shale-rich soils in the drainage basin. They've also found that a larger fan size relative to the drainage area creates more collapse. So a ratio of 0.25 to 1 is typical of these. And then a semi-arid environment. So we here in Utah live not too far from the mountain fronts. It becomes desert. If there's very little rainfall, you don't get a lot of runoff, so that's not a problem. And if there's a lot of rainfall, you have a lot of vegetation growing, which prevents a lot of rainfall. But the sweet spot for high sediment yield is in this like 23 to 30 centimeters per year. That gives us the highest settlement yield and more collapsible soil. We've collected data from about 500 or 600 soil samples in the Western US, and the soil type that shows up more typically is a silty sand, SM. That's 35% of our problems, and ML, silty, low plasticity silt, another 30%, and then CLML gives us another 15. So that gives us what, something like 80% of our problem soils. But we can also see that there are some in clays and clayey sands as well. This all depends on the geology of your environment. Well, so sometimes we think this is a problem that's only related to fine-grained materials, but we've found out there's also a number of case histories where gravels have collapsed. Soils that are classified as gravel, but then got wet and surprisingly collapsed. So this is one of the case histories. It's a cement plant in my state. And you may know that cement plants, these storage containers, silos, they are loaded with the products to make cement, and the loads can be very high. So on this side of this plant, they knew that they had fine-grained collapsible soils, and they designed it to be successful. But on this side, so you can see these enormous silos. The pressure on those silos footings was 860 kPa. So these under that pressure, even though these on this side it was gravelly soils that they didn't think would be collapsible, they had significant settlements and caused a lot of damage to this structure. So my students and I went in and looked at the case histories. We found 6 at this time, about 30 years ago. And what we found out is that the gravels might occupy from these case histories might have 30 to 50% gravel. Maybe there's also 40 to 60% sand in the mixture, maybe 10 to 30% fines. So even though it might classify as a gravelly soil, it's really the sand and the fines that are holding the structure, the gravel particles in a stable arrangement. So now that you know about this, you'll have to be aware that gravels can also collapse. We've been looking at liquefaction of gravels, and the gradation for these two things, for collapsible gravels and liquefiable gravels, are very similar. Others have put together, I'm not sure if this is over the top of your screen. Okay, others have put together charts that show the percent collapse as a function of the density and the liquid limit of the soil. And their approach was saying that if the void space in the soil is greater than that required to hold the liquid limit water is greater than that required to hold the liquid limit water content, then it's likely to be collapsible. So that's this given by E naught is greater than the specific gravity G sub S times the liquid limit water content at saturation. So that green curve, this was developed by Gibbs and Barra. That green curve shows that boundary. If you're below that boundary, it's susceptible to collapse. And if you're above, it's not susceptible according to this criteria. And we, from that data set we collected, we also found out where boundaries, rough boundaries of 5% collapse strain and 10% collapse strain might be located as well. So this could be helpful. Colorado, next state in from us, their geological survey has also collected data, and they've identified these boundaries that are based on dry density and moisture content. So if you're above this boundary, it's low collapse potential. If you're in this, it's moderate, like 3 to 5%. And if it's in this zone, which has low unit weights and low moisture contents, that would be higher collapse. We found out that these correlations are okay. They usually work, but there's a lot of uncertainty with them. And we find the best way, it's much better to take a sample of the soil if you can and test it in the laboratory. So we've cut trenches or excavated into a slope, cut a block sample, and we carve around it, and then put that shovel underneath there and break off the back face. And you can take that back to the laboratory and carve a ring sample that you can test in a consolidometer, an odometer. You have to be part a sculptor here. So it would help if you were Michelangelo type. These are very tricky because they're very brittle. And if you're not careful, you'll break off a piece that goes below the top of the ring. But if you are careful, you can get a good sample that you can test. We put it in the apparatus at the dry natural moisture content. And then we get to a pressure that we think our structure might be susceptible to, and we add water. And that causes a rapid change in void ratio. Okay. Now we can calculate the strain as being equal to the change in void ratio when water is added, divided by 1 plus E naught. So in this case, our initial void ratio E naught is 1, and the change in void ratio is about 0.2. So we'd have 0.2 over 2. So if this soil, that'd be about 10% strain. If the soil were to get wet at this pressure, it would settle about 10% of its height. So that can be devastating for the structure that you have sitting on it. Another approach is to use a double consolidation test. Here you have to get 2 samples just about the same void ratio. Then you load one of them dry for the entire load range that you're interested in, and you load another wet, so you get it saturated or wetted. And then the advantage of this is that you can look at what might happen at different pressure intervals and calculate the change in void ratio and get the strain that would take place at different pressures. So this could be very useful. It's more useful, but it's twice the cost and time. Well, sometimes it's really difficult to get an undisturbed sample, and this is the case when we have gravelly soils. So you can see those gravel particles on the sidewall of this excavation, and there's just no way you could get an undisturbed sample from a drilling rig. Or even if you tried to get a block sample, you'd probably be unlikely to do so. And the gravel sizes might be too large to put in your ring consolidation test. So in this case, what we've done is plate load tests. So we have a plate at the bottom or on top of the soil. We put our impervious steel ring around this, and we can test it in the dry native state. That's this blue curve right here. And then we can flood the soil with water at adjacent site and see what change there is in stiffness of the soil. If it's collapsible, you'll see that there's a dramatic difference in the stiffness and the failure pressure for these collapsible soils. So you could do this plate load test. You're probably already thinking, yeah, but that's only going to test the top section of the soil. And you're right. That's the weakness of this thing. Bill and Sandra Houston at Arizona State have developed a downhole plate load test where you can drill to the depth where you're concerned about. You put this small plate inside the borehole here, and it's attached with the drill rods to the top. You can apply different weights to produce the desired pressure at the base and see how much the soil settles under that applied pressure in the dry state. And then you can pour water down this port so that you can saturate a known thickness of water of soil below that level and see what kind of settlement you would get due to addition of water. So this is a very handy test to investigate what might happen at different depths. Another test that we've used is the borehole pressure meter test. In this test, you have a rubber membrane with metal fins or sheath that protect the rubber membrane from being damaged. And you can expand that pressure meter membrane and get a relationship between pressure and volume change. So in this test at this collapsible soil site, we did one test where the soil was dry. That's this blue curve here. You can see it can develop significant pressures at small volumes. Then we did another test where we wet the soil prior to doing the test. You can see the dramatic difference in pressure with volume here, indicating this certainly is a collapsible soil. Another way to do this in one shot would be to load the pressure, apply pressure to increase the volume until you get to the pressure you're interested in the field, and then drop water down into the soil. And you can see how much change in volume there is under that same pressure. If it's not collapsible, it just would continue on up and be relatively unaffected by that water. So there's a few tests that you might have. So have you ever noticed in life that it's easier to find a problem than to solve a problem? I'm very good at finding problems. It's much harder to solve the problem, right? So the reason we're engineers is that people think that we can solve their problem, right? So we're going to spend more time about collapsible soil mitigation now. How do we solve this problem? Before I go on, I want to remind you that these are metastable structures, as we were talking about. They might be just stable enough to hold your structure up in its dry native state. But if you fail to consider metastable structures, so I'll give you a metastable structure and there might be visible. You could end up a dead dog, right? So you have to be careful with these kinds of things and do your homework and do a good job. So let's look at If I was there in person with you and we could easily talk back and forth, I'd ask you for suggestions because I think you know most of these already. We could prevent wetting of the soil. That seems like a smart thing to do no matter what you do, is try and prevent it from getting wet. We could excavate the soil and recompact it. A lot of these soils would be just fine if they weren't so loose. We could pre-wet the soil in place and maybe pre-load it so that it's settled under the final load that we're going to apply. Fourth, we could use deep dynamic compaction to compact the soil in situ with heavy weights dropped from a large height. We could use compaction grouting, where we try and compact the soil horizontally. We could also use injection of sodium silicate to cement the soil particles together and make them less susceptible to collapse. And if none of these things work, then we could go to a deep foundation, but we'll have to be concerned about some other issues that we'll talk about there. So that's some of our solutions. My guess is that you have other solutions that have worked for you, and I'd be happy to learn about those too. So preventing wetting, we want to have positive surface drainage. So instead of having flat surface like this, certainly not like that, it's going to lead water to come into our structure. I see these still around here in Utah where we have this problem all the time. We want to have a positive slope away from the structure, right? If there are roof drains, we certainly don't want them to empty out right on top of our foundations to wet our soil and have it collapse. We want these drains to extend out away from the structure and hopefully be carried away to a drainage canal. Some people have used impervious membranes located underneath the soil to prevent water from getting in. And another technique is xeriscaping, where you, in America, you often see people in dry, arid regions try and recreate lush climate, and they have lawns they have to water 3 times a day, and that can lead to a lot of problems with their structures. But it looks more like this kind of thing, and I think people need to appreciate the beauty of the desert environment as well. And this can solve a lot of the problems. Excavation replacement. It could be complete or partial. Ideally, it would be complete. You would excavate out all the soil that was collapsible, but that might be too expensive, and you might take a gamble that you could excavate part of it out. The collapsible soil can be used as a fill. It's desirable because of the higher fines content that prevent water from getting through it. We typically compact to 95% of the Proctor maximum unit weight standard. And then we want to usually fill to twice the footing width and at least 1 footing width deep, so that we cover the shear zones that might develop. So when could we get away with partial excavation? If the soil is maybe 3 meters thick or less, we would probably excavate it in the United States. This all depends on the cost of replacement and the value of the structure we're trying to protect. But if it's maybe 6 meters deep, that'd be a difficult thing to do, maybe too expensive. So we could put compacted fill under the foundation and put it deep enough so that the pressure on the fill or pressure on the collapsible soil is low enough that it wouldn't cause a lot of collapse if it were to become wet. So some of the advantages of doing this is it reduces the thickness of the collapsible soil above what it was originally. It increases the depth that water has to penetrate through the compacted fill to cause a problem in the underlying collapsible soil. The compacted mat tends to reduce differential settlement, so our footings don't tilt. And it also reduces the induced stress in the underlying soil. We have to recognize, though, that water penetration can still cause a lot of settlement, even if the induced stress is low, just due to settlement under the vertical effective stress. So if we can't just do that, maybe we go to another strategy of pre-wetting. So we may build some small berms, maybe they're a meter or so high, and then we fill that berm up with water and wait for it to percolate into the ground. And we can fill it back up, let it sink into the ground again. And eventually in this process, we might be able to wet that soil. So, of course, it always goes like that, right? Just straight down, just like we expected. You might have some problems with this occasionally. So this is useful when you're not putting on a lot of additional load, like you might have a roadway or a canal. If you're going to apply significant additional loads, then the soil should also be preloaded with a fill. And you might have problems if there are low permeability layers underneath your area, which would cause the soil to move horizontally rather than penetrate deeper. And we've had cases where we've put in vertical drain holes to get deeper infiltration. One of the major case histories talking about pre-wetting for soil is the California aqueduct that takes water from Northern California to Southern California to handle their drinking water needs. And it's quite a structure, as you can see here. Now, as part of that, they did some tests at the Mendota test site in Fresno, where they had some benchmarks and some berms, and they let water sink into the ground. As you can see on this test area on the left side, they pre-wet the soil for 14 months, and it extended down to 40 meters. It's very deep collapsible soils. And you can see the settlement taking place around the center of that area on the photo on the right. And the collapse was more than 3 meters of settlement, more than 3 meters, or about almost 8% collapse strain. So you can imagine what would have happened if they had built that canal on top of this soil and it got wet with all that settlement. It would have been a major problem. So in significant areas of the aqueduct, they pre-wet and prior to building the canal. Another technique is deep dynamic compaction, or DDC for abbreviation. And here in this process, we're dropping 20 to 30 metric ton weights from a height of maybe 15, 25 meters or so. And the soil is compacted by the impact as well as the stress waves that go down into the ground. So you might have seen that this dynamic compaction technique has given rise to a new extreme sport. Maybe you've seen this in Saudi Arabia as well. I don't know. This guy is pretty brave, I think. So as you probably guessed, that's probably a fake, right? But it looks pretty fun. So there's in the United States, there's a lot of collapsible soils in the West, and all these projects here, I think there's maybe 10 or 11 of them, are cases where dynamic compaction has been used to treat collapsible soils. And often they're highway projects. There's some for hospitals and for just regular buildings. And then in Avenal in California, this was a prison that they were treating. So the typical deep dynamic compaction drop pattern is shown here. You might have some primary drops in the blue, and then you would come in with secondary drops in the red, and the spacing is typically about twice the diameter of the drop weight. So here's a drop pattern for 12-meter wide pavement width in interstate highway in the state of Wyoming. And their approach was to put in these primary drops, 3.7 meters in one longitudinally and 3 meters transverse. They put did 5 to 6 drops at the primary points and 2 to 3 drops in the secondary points. The average crater extended a diameter of about 3 meters. So if we compact all the way around with that crater size, we'd likely get most of the soil compacted. So here's some photos of the DDC craters after the first pass on this roadway. And you can see that it's, you're getting some pretty deep craters, right? This is about 6 feet deep after the end of dropping. And this is after the second pass. And you can see they've lowered the level of the roadway by about 1 meter, this process. And then the problem becomes how you deal with that loose soil that's left over. So one way is to use what they call ironing passes and compact this soil with a lighter weight. So if your primary compaction pass produces something like that, you can go in and either use the dynamic compaction to compact it down or use roller compaction, conventional roller compaction to compact that surface layer. And that's where most of your stress is going to develop. So you need to be sure you do that top right. Then you can put the subgrade and asphalt or concrete paving in place for your roadway. So this was used, as I said, in Wyoming. Now, most of the time the soils are pretty dry, but we've had some problems on this project particularly where we had some wet soils in a drainage area. In the drier soils, the typical craters were 1 to 1.5 meters deep. In the wetter soils, they could be 2 to 3 meters deep. And this causes some real problems because the crane operator can't pull the weight back up out of the ground if it's too wet. So these measurements of the settlement that took place were from something like 20,000 drops of this impact crater. They had an intern student come work for a summer and measured all these drops. I don't think it's a big surprise that intern student decided not to go back to work for the Wyoming Department of Transportation. Can you imagine? The first day would be kind of fun, but then 3 or 4 months, just every day counting all the drops and depths. That's not what engineers are good at, right? So this is an aerial photograph of the treatment of Avenal Prison with the DDC project. This was around the clock effort to get the prison built on time. And they had 2 cranes here operating. I called the warden for the prison to ask if I could get some of the soil data for this study I was doing. And you can imagine that if you're in charge of a prison, you might be reluctant to give out soil information to some random person who calls you on the phone. But anyway, I was finally able to convince him that I really was a professor and that I needed this for a study we were doing, and he gave it to us. This is dynamic compaction at a national park for a new visitors center. This is a fun place to be doing some inspection work because you can see all the beauty around you of these tall mountain spires. One of my students developed this equation that gives you the estimate of the crater depth. It turns out all these factors are statistically significant. So the crater depth is related to the number of drops, the height of the drop, the weight of the drop, the spacing, and the contact pressure. So if you have that information, you can make an estimate of how deep the crater would be that you'd create. And this is the measured versus calculated depths, and they're looking okay. But note that that's a log. Those are both log scales. So it's probably not as good as it looks, but you can see it's doing all right, except for these points. And these are points where we had a high water content. We're getting much higher craters than we expected. You want to know how deep you can treat the soil. So we're going to try and come up with this parameter called Dmax. This is the depth to which you don't get any more improvement. So that would be where the penetration resistance before and after are basically the same. So in this case, it looks like we've got to maybe 4.5 meters or something like that. That's the depth of improvement, Dmax. And here's a couple projects. So we can see in this on the left in New Mexico, we are getting back to, well, maybe get 8 or 9 meters. Then this one in Richfield, which is a lower hammer weight or drop weight, we're only getting treatment down to about 5 meters. So we took all the information we could get from the Western US and used this equation that's been suggested before to get the Dmax is equal to this coefficient N times the energy, the weight times the drop to the 1/2 power. And these are some typical coefficients for granular soil, silty soils, and dry clays. That goes, the coefficient goes lower as the soil becomes more fine-grained. And here's all our data points put together. You can see there's a scatter about the mean here, but for collapsible soils, the depth D that we're getting the maximum improvement is about 0.4 times WH to the 1/2 power. And then the scatter is about 0.55 to 0.25 for all the data in the curve. This is my graduate student, Jiyoung Kim from South Korea. She helped me with this research study. And this is showing the normalized depth within that zone of treatment, D, and on the y-axis. And on the x-axis, we're getting the percentage of the total improvement that we've obtained. And you can see that it's not just linear. In fact, it looks like we're getting about, I called these the Kim curves for all her work on this study. We're getting about 80% of the improvement, 80 to 90% of improvement when we're within the top 2/3 of the zone Dmax. Okay. So if I were doing this on a real project, I would calculate that Dmax, and then I would make sure the depth I needed to treat effectively was within 2/3 of that Dmax zone, because that's where I'm really going to get most of my improvement taking place. With dynamic compaction, you have to be concerned about vibration, and you don't want to cause damage to any adjacent roadways or buildings. So you want to monitor the vibration values that are being produced. So you can use some charts like this. This blue line is the upper limit for non-collapsible soil, or sorry, the blue line is the limit for non-collapsible soils, and this, all the data points show our equation for the peak particle velocity as a function of the energy divided by the spacing or the distance you're out d times 20. And this is plotted, peak particle velocity is plotted on an inverse scale distance. So the further you are from the drop point, the lower the vibrations are, and the closer you are, of course, the higher they are. So our curve runs like this. It's much lower than what Paul Main suggested for non-collapsible soils. And this is because that soil absorbs a lot of energy as it's as you're dropping the hammer into it, dropping the weight. So then you can compare that to barely perceptible values and maybe target energy that you'd like to use so that you don't cause any cracking in houses that will be close to this site. So these kind of things are this velocity information is very useful in planning your project. Even if you feel comfortable that there's no problem, my advice to you is always measure the vibrations when you're doing these in a real project, because invariably someone is going to complain that you caused damage to their structure, even though there's no chance that that happened. If you have the evidence that the vibrations were just too low to cause a problem, you'll be able to eliminate the concern. So for the energy you need to use for standard, for non-collapsible soils, you might apply 33 to 50% of the standard Proctor energy to get the treatment that you're after. And that's low enough because the soil has already been compacted by natural processes. If you're dealing with collapsible soils, the energy that's required could be much higher. We're seeing 40 to 100% of the standard Proctor energy. I think I showed that already, but some problems in applying DDC. If you have higher plasticity soils, PI is greater than about 10 or 15, it might be difficult to get energy down through that into the collapsible soil. If the soil profile is very dry or very wet, again, you might have difficulty getting the energy through the profile. Sodium silicate, this is where we combine, we inject silica into the soil structure, and it combines with the salts that are typically in this structure to form an insoluble cementitious gel. The Russians use concentrations of 20%, makes it very expensive. But in our test, we've just used 2% concentration. And at this low concentration, it can infiltrate the soil and be relatively inexpensive. If you get, the higher you get, the more expensive it is, but it turns out to work quite well, as you'll see. Another approach is compaction grouting. So here you, on a grid pattern, put a pipe down into the ground and you inject low slump cement grout into the soil and apply it under pressure. So it moves horizontally and compacts the soil around it. Then you come back to another zone to the side of it, do the same process all around, and you eventually get the soil compacted to where it won't be collapsible. This is a nice way of controlling what's really going on. And lastly, if you just don't think any of these techniques are going to work, or they're going to be questionable, they'd be too expensive, you could go to a deep foundation. So the idea here is use drilled shafts or driven piles, and you drive through the collapsible soil into a non-collapsible soil. Okay. And then the applied load is resisted by the positive side friction along the shaft, of course, and the end bearing or the toe resistance of the base. But you have to think a little more about this, because the wetted zone is going to extend deeper, or might, the soil might around the foundation could become wet. And if it becomes wet, then the soil will still settle downward, and this could produce a negative friction on the side of your shaft. So that could lead to an additional load that you've got to consider. So in my work, I always like to do large-scale tests to see how things are going to really work. So we received a grant from the National Science Foundation to study mitigation measures for treated soils. And this is a site in Nephi. And you might be able to see that it's at the bottom edge of this alluvial fan here. And there's our test area right here. Okay. The soil properties here are, it's a sandy silt with thin gravel layers, 70% silt, 20% sand, 10% clay. It has a plasticity index of 6, so we thought this would be a good test site. It's mud flow deposits at the end of the alluvial fan. The soil is 6 to 9 meters deep. So at this site, a farmer let us use his property, Mr. Wynn. We're very grateful to him. And we did one site that was not treated, another site where we pre-wet the ground with water, another site where it was pre-loaded or pre-wet with sodium silicate. We had one where we used partial compaction with compacted fill, one with dry DDC, and one with wet DDC. So let me walk you through here quickly. At each of these test areas, the area was called Nephi. We had a 1.5 meter square test footing, and we applied 86 kPa with these highway barriers sitting on top of the footings. So at each test area, we had monitors to tell us the settlement at 0.9, 1.8, and 2.7 meters. There's our square footing. It's 2 slabs, 30 centimeters thick. And then we had these soil berms that were 60 centimeters tall, and we'd fill these up with water, as you see here, and let the water percolate into the ground. We had a downhole nuclear moisture gauge that told us the water content around this aluminum pipe. And then we did a survey to see how much settlement was taking place. So here's showing the progression of the wetting front as we add more and more liters of water. You can see we go from this dry condition here out to where we're getting about 17 to 20% water content, which is about 80% saturated, okay, down to 3 meters or so. So here's the footing performance in the untreated area. We left one night, everything looked fine, put the water in. We came back the next morning and it had settled so much that it started tipping to one side. Maybe you can see that. This is what it looked like after we'd put in about 4,000 liters of water. And it had settled 30 centimeters on one side, and we had 10 centimeters of differential settlement. Wow, that would be terrible if you had a structure supported like that, right? We tried our very best to get the loads put on the center of the area, but even though the load was applied in the center of the footing, we still got this differential movement. We had another area where we pre-wet the soil. We allowed it to settle. You can see the cracks from the settlement of the ground. We had maybe 70 centimeters, not centimeters, 70 millimeters, try that, 70 millimeters of settlement that took place while we wet the soil here. We let this dry out for months, and then we applied the load to the footing. Things are looking good. But then when we put the water back in, left a bad aftertaste, I'm saying. So we got almost the same amount of settlement for the site we'd pre-wet, even though we'd seen 70 millimeters of settlement take place. Well, if you think about it, most of the settlement that happens when you put this load this foundation is occurring right underneath the foundation within a footing width under the footing. The settlement that was taking place when we pre-wet the soil was deeper in the profile. So the pre-wetting had never really compacted the soil over the whole zone that's going to feel stress from the structural load. So if you wanted this to work better, you probably should pre-wet it and apply a surcharge of soil to get it to settle under that pressure. This is a partial excavation replacement. It's about a meter of soil. I think we over excavated and compacted with this soil. You can see it's a silty gravel. And things were looking good. We applied a lot of water here and very little settlement. But as we continue to fill it with water and let the water percolate down in the ground, the water eventually penetrated through the compacted fill, and then we had 15 centimeters of settlement take place. Okay. So if your client wants to try this, they should be aware of the hazards that the risk they're accepting, and everyone should know what the cost could be of saving money on the construction. Surprisingly, though, in contrast to those other cases, can you see that the settlement was uniform? No tilting was observed. This is the test area with sodium silicate. We let water percolate down into this profile as well. We got some settlement taking place with the water infiltration. But when we put the foundations in place and then re-wet the soil, we had settlement less than 12.5 millimeters. So this was a success story. And very minimal creep. We left these on here for several months. Then let's look now at the dynamic compaction. This is our layout. We had 5 drop locations. The drop area was about 1.2 meters, or the drop width. And there were about 2 diameters or 2 widths apart, center to center. So in our compaction process, this was a lot smaller than a big project. A 5-ton weight dropped to 21 meters, 7 drops per drop point. So this is our crane operator came out to the site. He said, what is it you want me to do? I said, we want you to drop that weight. There's ground improvement companies that do this, but we just asked a crane operator. He said, they told me in crane school never to drop a weight. That would be a disaster. I said, we want you to do it about 100 times. He said, okay, I'll try, but he has to apply the brake just to the right time as it hits, or his cable spools all out and it becomes a real difficult process to get it back in. So here's a drop. So again, we're monitoring the drops. Okay, so that was on the dry soil. You can see there's this big cloud of dust, and that can be a problem as well. You may have to wet this down to keep the dust down. The other project, you remember, we wet the soil, and when the compactor, when the crane came to the site, the soil that we had pre-wet hadn't had enough time to completely dry out, and it's still pretty wet. So you'll see the result of that. Let's go ahead to this one. You can see the big craters. This is dropping into the wet soil. The site, the weight almost disappeared. And you can see it's a struggle to get that back out of the ground. Sometimes you might have to change the, and that time it did disappear. It went 2 meters into the ground. All right, so that's the hazard of doing this dry. So this shows all the crater depths that we're developing. After about 6 or 7 drops, you're not doing much more. The crater drops, crater depths are bigger in the center of the test area. Each one of those locations, we monitored the void ratio. We did CPT tests and pressure meter tests and collapse tests of these soil underneath the drop and in between the drop points. The initial void ratio is shown in red. We have a void ratio of about 0.9 to 1. Underneath the drop hole after treatment, our void ratios dropped to about 0.6 to 0.7. And big, very effective. In between, we're treating down to 3.5 meters, reducing the void ratio substantially. So here's the foundation performance after the dry DDC. We wet it with the same amount of water you saw previously. Everything stayed in place. Settlement was less than 2.5 millimeters. We let it sit on those weights sit for 6 months, I think it is, and then we had a total of 8 millimeters of settlement. So there's some creep that's taking place. Here's our DDC after pre-wetting, like you saw, our drop weight disappearing. The crane operator said, okay, now your weight is no longer 5 tons, it's 6 tons. So it's all soil additional weight. This compares the treatment in red with no treatment, 300 millimeters of settlement. With dry DDC, it's, like I said, 12, 15 millimeters, even after creep. I guess that was 8 millimeters. And what dynamic compaction, we got 50 centimeters of 50 millimeters of settlement. So we thought, well, we could be a little more effective, and this is the last thing I'll show you, that is that if we get the right moisture content, it might be a lot easier to compact this. And you can think from your elementary soil mechanics class, as you increase the compactive energy, the water content, the moisture content, optimum moisture content goes down, right? As the energy goes up, the moisture content for optimum compaction goes down. And in our project, our energy that we're using is closer to about 1/3 of the standard value. So we went into the field and tried to create 6 test cells with different water contents. And it turns out that it's easier to get a water content close to the optimum than it is to get these other water contents. So we played around with enough to get a variety of water contents. This will show you a comparison between water content at 7%, which is very dry, and we're only getting improvement down to about 3 meters, 10 feet. And then at the optimum moisture content on the right side, we're getting improvement down to almost 6 meters, and the change in void ratio is much greater. So if you can get the water content at the optimum value for the energy you're using, you can be much more effective in the compaction. Now, the ground improvement contractors have techniques where they can inject a specified amount of water and do this. In our project, we are showing here a rather complicated slide, but in each one of these curves, it's showing you the dry density that we're producing as a function of moisture content. So the first one we're starting out with is up here, where the energy is high and the optimum moisture content is more like this value here, right? As the depth goes, as the depth increases, so as we go down here from 1.2 to 1.8, 2.4, 3 to 3.7, less energy is getting into the ground at that depth. And so the optimum moisture content for compaction is higher, right? So down at 3.7 meters, the optimum moisture content is about 17%. And at the ground surface, the optimum moisture content is 13%. So a ground improvement contractor, by injecting a specified amount of water, could increase the efficiency of your compaction project significantly. All right, let me conclude then. So no matter what mitigation strategy you're going to use, you should always make every effort to prevent wetting from taking place. Pre-wetting is likely to be successful only if you're not applying an additional load. If you got additional load, you want to surcharge it as well. Excavation and replacement is probably the most common economical approach for shallow layers, maybe less than 3 meters or so. If it's more than that, then the DDC turns out to be more efficient. If you're only going to replace part of the soil, everyone involved should understand that this is a calculated risk. And if you have a high runoff event or a break in a water pipe or something like that, then there could still be problems. The DDC is probably the most economical and effective method for treating deeper soils. You'll have to look at your local contractors, and sure they can give you some information about that. But it is very effective, we've seen. And the deep foundation approach can be very successful as well, but it needs to account for the potential for down drag or negative side friction to increase the load. And you'll need to make sure that doesn't cause excessive settlement as well. All right. Well, thank you for your attention today. I want to remind you, when you're a foundation engineer, you don't take any unnecessary risks like this couple that scares me to death. I'm risk averse. So do everything you can to prevent problems from happening. I've included in this presentation a list of the references that talk about just about everything I've discussed today. I'll send this on through to Mohamed, and Dr. Mohamed can provide this information, this list of references, and the slides in the presentation to any of you that might want to get it.
Thank you so much, Professor Kyle. Really, the presentation is very valuable and informative. As usual, your full-scale testing is remarkable all the time. I always love to read your full-scale paper, field testing papers. Yeah, most of the cases in different topics is very informative, include all scenarios, which is very, very beneficial to any reader. Thank you so much for this wonderful presentation. And thanks for exploring the Saudi geographics. The map you presented at the beginning of the presentation is indeed the explored location that contains collapsible soil. And by the way, the Saudi design standard also mentioned this map and recognized the collapsible soil as one of the problematic soil identified within Saudi Arabia. This could explain the large number of questions we have in the inbox here. Many of the attendees would like to ask several questions, but most of them are rounded about one main topic. There is here one kind of soil called sabkha. I'm not sure if you are familiar with the name or not. It's also one of the collapsible soil with high saline. Most of them asking, is it considered as a collapsible soil, and what is your recommendation for treating such soils?
My understanding of that material, it's created by salt, high salt content that's acting as a cementing agent.
Yes, right.
Is this the situation? I think it's likely to have similar characteristics to the cemented soils that I've talked about. It's probably not a pure loess, because loess is wind-blown deposits. So I think your deposits are more, they may be windblown. I don't know for sure, but I think the wetting of those soils and the reduction of the stiffness of the soil that results is probably very similar to what we observe for cemented soils here in the United States. So I think these same approaches would be successful. If there's less fines in the mixture, they may be even more successful than what we see for the dynamic compaction with fine-grained materials. But I'm a novice when it comes to this kind of material. I'd be interested to learn more about it and see if I could help you in your efforts to deal with it. Maybe you have a project that I could come work on, Mohammed. That would be
Yes, sure.
fun to see.
Sure. For sure, we will send you some information about this soil and some tests that were conducted on some samples. It's our pleasure to have you in one of the projects. By the way, it's we find this soil in many locations in Saudi Arabia. That's why many of the attendees asking about it. I will share some information with you about it.
Thank you. That would be great to see. I ran across it when I was looking at some of the papers on collapsible soil in Saudi Arabia. So I know it's a big problem for you.
Right, right, and even in Riyadh and many big cities, we find collapsible soil at several locations. Yes, and we just take one step here for the recommended solution before going to the deep foundation after. Passing by all scenarios you presented today,
Yes.
we might explore the visibility of the rigid inclusion and the
Oh,
CMC
yeah.
before going to the deep foundation.
Yeah.
Uh, yes, and indeed, the negative skin friction is also a concern at that time. It's similar to the
Yes.
miles as well. Yes. Uh, we don't know how to thank you for this wonderful lecture. Personally, I really enjoyed this lecture. I know we talk a lot of your time, but feel free to give us some words before we close this session.
I appreciate the invitation to speak to you. As a professor, my desire is to spread all the information I know about to anyone who is interested, and I'm always delighted to talk to people who have similar interests to mine. I also want to say at this time where that seems like our world is sometimes divided by war, that my feeling is that love and friendship and cooperation can always be stronger than the hatred and bitterness that we're seeing. And my wish is to be your friend, and I want to be your friend and colleague, and hope that that can be the attitude that we feel throughout the world, instead of this bitterness and that we sometimes see in bad moments. So thank you for the invitation. I hope what I said was worthwhile and useful to you. And
It was very
hopefully
beneficial.
we'll meet in person in the future.
Yes, we have a conference in the early next year. For sure, it's our great pleasure to have you physical that time. For sure, we will invite you for this conference to give us another wonderful, but this time not be a lecture, it will be a keynote speech about
Ah,
one of the wonderful full scales testing you are always conducting. Thank you so much, Professor Kyle. It was a great pleasure and honor to have you today.
thank you very much.
Thank you. Thank you for all our attendees. We hope the lecture was very beneficial to all of you. By the way, we had a large diversity today, many geotechnical engineer and civil engineer from different companies and organizations from Saudi Arabia and other Arab countries, and also beside our student and faculty. Thank you so much, Professor Kyle, and we hope we meet you physical very soon.
All
Thank
right.
you.
Bye-bye. Have a
Yes,
great week.
you too. Bye bye.